You know, every single app on your phone, every website you visit, it all started out as just a simple idea. But how did they go from that to serving millions, even hundreds of millions of people all at the same time? Well, that is the science, or maybe the art, of system design. And today, we're going to pull back the curtain and demystify how it all works.
Really, it all comes down to this one question. How does an application, maybe one that started on a single developer's laptop, handle that kind of explosive growth? How does it serve millions of users without just completely crashing and burning? That's the puzzle we are going to solve together.
So here's our game plan. First, we're going to talk about scaling your application. Then, how you direct traffic from all over the world. After that, we'll dive into how all the different parts of the system actually talk to each other. Then we'll get into the really important stuff, storing and managing data. And finally, we'll see how you build these things to be super reliable. So, let's get started.
All right, so our journey starts with what is honestly the best problem you can have: success. You've got more users than you ever dreamed of, but all those users mean more traffic, and that simple little setup you started with, yeah, it's not going to cut it for long. This is where scaling comes into play.
You know, at its core, scalability is really just about one thing: handling growth. As more and more users flood in, you've got to add more resources, more power, to keep everything running smoothly. But the big question is, how do you actually add that power?
Well, you've got two main options here. The first one is called vertical scaling. This is kind of like upgrading your own computer. You take your one server and you just beef it up. Add more RAM, a faster processor, a bigger hard drive. It's simple, but you'll eventually hit a wall. The second option, and this is what all the big apps do, is horizontal scaling. Instead of one giant, super-powered machine, you just add more machines to share the work.
And the reason horizontal scaling is the go-to strategy is really simple. Like this quote says, you can just keep adding more and more servers. There's virtually no limit. But there's another huge benefit: redundancy. Think about it. If one of your servers fails, the others are still there to just pick up the slack. Your whole system doesn't crash.
Okay, but if you have a whole bunch of servers, that creates a new problem, right? How do you spread the incoming requests evenly? You need a traffic cop. And that is exactly what a load balancer does. It's a server that sits out front and cleverly directs traffic to all your other servers, making sure no single one gets overwhelmed. It might just cycle through them one by one in what's called a round-robin approach.
All right, so we've got our little army of servers, all ready to handle a ton of traffic. But what if our users are all over the world? A user in Tokyo shouldn't have to wait for a signal to cross the planet to a server in Texas. So how do we get everyone connected as fast as possible? A massive piece of this puzzle is something called a Content Delivery Network, or CDN. Think of it like a global network of local warehouses. These servers store copies of your app's static files, things like images, videos, all the heavy stuff that doesn't change much. So when a user in Japan requests an image, they get it from a nearby server in Asia, not all the way from the US. It makes a huge difference in speed.
But wait, how does your browser even find that server in the first place? When you type in a website, your computer uses what's called the Domain Name System, or DNS. It's basically the phone book for the entire internet. It takes that nice, human-friendly name you typed and translates it into a machine-readable IP address, which is the server's actual street address on the network.
So, once your browser has the IP address, it needs a super reliable way to talk to the server. And that's where TCP comes in. You can think of TCP as the internet's postal service. It takes all the data for a website, chops it up into tiny numbered packets, sends them out across the network, and then, this is the magic part, it guarantees that they all arrive and are put back together in the exact right order on the other side.
Okay, so our users are now connected to our servers. That's great. But now, we need to look at how the different parts of our application actually talk to each other. They don't just shout random data into the void, they use very specific protocols and patterns, almost like they're all speaking a shared language.
So while TCP is handling the low-level, reliable delivery, making sure the mail gets there, what developers usually work with is a higher-level protocol called HTTP. This is the language of the web. It's a really simple model. Your browser, which is the client, sends an HTTP request asking for something, and the server sends back an HTTP response with the content. But even within our own system, different services need different ways to talk. REST is kind of the universal standard. It's flexible, it's reliable, everyone knows it. But for, say, a mobile app, you might use something like GraphQL, which is amazing because you can get all the data you need in one single super efficient request.
And for crazy fast internal communication between your own servers, you do something like gRPC. It's all about using the right tool for the job.
So all this scaling and communication is great, but it's pretty useless if our system has the memory of a goldfish. So now we're going to talk about the absolute heart of any application, how it stores and manages its data.
For decades, the absolute gold standard for making sure your data is safe has been something called ACID. It's a set of 4 guarantees. Think about a bank transfer. Atomicity means the transaction is all or nothing. The money can't just disappear. Consistency means the data always has to follow the rules. Isolation means 2 transfers happening at the same time can't mess each other up. And durability means once the transfer is done, it's permanent. It's saved for good. But that level of safety and perfection can be kind of slow when you're operating at a massive global scale. So a totally different model emerged, called Base. And it makes a huge trade-off. It basically says, we're going to sacrifice perfect up to the millisecond consistency in favor of being fast and basically available all the time. The data will all catch up and become consistent eventually.
And this philosophical divide is really at the heart of the 2 main types of databases you hear about. SQL databases, which are relational, think spreadsheets with rows and columns, are typically built around that super safe ACID model. On the other hand, no SQL databases, which are non-relational and more flexible, often follow the base model. By giving up that strict consistency, they become way easier to scale horizontally across tons of machines.
So how do you scale a massive database horizontally? Well, one of the most popular ways is a technique called sharding. You literally take a gigantic database and you break it up into smaller, faster, more manageable chunks called shards. For example, you could put all your users from North America on one shard and all your users from Europe on another. This lets your database grow almost infinitely, just like we did with our servers.
Okay, we've done it. We've scaled our servers, we've scaled our database, we have millions of happy users. But here's the scary truth. With this many moving parts, things are absolutely 100% guaranteed to fail. So the final crucial piece of the puzzle is designing a system that actually expects failure and can handle it gracefully.
2 key strategies make this possible. First is replication. You never ever have just one copy of your important data. You have lots of copies, constantly being updated. Then you have failover. This is the magic part. If your main database server, say, literally catches on fire, the system is smart enough to automatically switch over to one of those healthy backup copies. And it often happens so fast, your users don't even notice anything went wrong.
And this all brings us to a fundamental law of distributed systems called the CAP theorem. It's fascinating. It basically says that in a large system, when there's a network problem, and there will always be network problems, you can only have 2 out of 3 things: consistency, availability, or partition tolerance. Since you have to tolerate network partitions, you're forced into a tough choice. Do you prioritize consistency, making sure the data is always perfect, or do you prioritize availability, making sure your site is always online? You can't have both. And that leaves us with the core dilemma that every single system designer has to face every single day. If you're building a bank, you're always going to choose flawless data. But if you're building a social media feed, you're probably going to choose having a system that's always on. There is no single right answer. And this constant, difficult balancing act of trade-offs, well, that's what system design is all about.